Hello and welcome to lab. Today we're going to do experiment 14, Le Châtelier's principle. And this experiment deals with the equilibrium position of reactions. We'll be able to detect most of the equilibrium positions via a color change. I'd like you to be my lab partner, and I'd like you to follow along with me in your lab manual. So it might be helpful to maybe remove the data pages from the manual or put a sticky note there so you can easily flip back and forth. Let's start in with part A, the chromate-dichromate equilibrium. We'll take our first test tube, and in step 1 it says at approximately 1 milliliter, or 3 milliliters, which is about an inch, about the length of the joint of your thumb, first joint of your thumb. And again, it's not critical, the amount. We're just getting enough so that you can see it. And that looks like a good amount. So I've added my potassium chromate to my first test tube. And you can read in the directions here and then populate the very top of your data table with the ion color. We know that our chromate ion is yellow and our dichromate ion is orange. All right, in the second step it says add 3 to 5 drops of sulfuric acid. And I've got all my reagents that I need in a tray here. That should be enough. I added 3 drops. And you can give it a shake either by flicking it, shaking it. We do have a stirring rod, but we'll use that later. And you can see that the color is orange. Just put against a white backdrop. It is definitely orange. Okay, so it says mix, record any observations, and answer the data question QA1. All right, so we'll do that. In step A3, we can say the stress on the system, and we added sulfuric acid. Sulfuric acid is made up of hydrogen ions and sulfate ions. Now the first thing you're going to ask is, do I see either the hydrogen ions or the sulfate ions in my balanced net ionic equation that is at the top of the data sheet? And yes, I do see the hydrogen ions. It's on the reactant side. So the stress on my system is going to be adding, either word, H plus. All right, so add H plus. And the direction of the shift, you saw that it was orange. So you can either put right or draw the right arrow. And the observation is the solution turned orange. Now let's answer that question, QA1, and we are going to answer the interpretation question. And I'm going to go over this whole first sheet with you, and so you'll word it in exactly the wording that I need it in. And the wording that we need for this one is adding a reactant shifts the equilibrium to the products. Okay, we saw that. We added a reactant, H+, and it shifted the equilibrium to the products, and we saw a visual example of that because it was orange. So adding a reactant, H+, shifts the equilibrium to the products. Okay, let's move on with our next step, which is step 4. Add 10 drops of sodium hydroxide. I can always find the sodium hydroxide easily because it is in the plastic bottle. Sodium hydroxide, etches glass, so you'll always find it in plastic. All right, I just added 10 drops, and it doesn't even look like I need to mix it. It says I do. So you can see the equilibrium there. I'll put it in front of a piece of white paper to make sure that you also see the shift in color. All right, so let's answer A5 here. What is the stress on our system? I added sodium hydroxide, NaOH, so it's either the Na plus ion or the OH minus ion. Do I see either one of those in my balanced net ionic equation? I do not. But can one of those react with one of the species in the balanced net ionic equation? Yes. How about the OH minus ion? And I'll give you a hint. It's never going to be the Na plus ion. All right? That will always be soluble in solution and will not react. So if I have the OH minus ion, what could it react with? How about the H plus ion? All right? And the stress on the system will be adding OH minus. The direction of shift, hopefully you have a left arrow because now you see the color of the reactants. And the observation over in this column is the solution turned yellow. Now, I need to answer QA2, the question in the large box here. Explain what is happening in terms of Le Chatelier's principle. Well, what did we do? We removed a reactant. So removing a reactant shifts the equilibrium to the reactants. Removing a reactant shifts the equilibrium to the reactants. Okay, and it says support this explanation by writing the balanced net ionic chemical equation of the sodium hydroxide reaction. I'll give you the ions and then I'd like you to balance it. So we have our OH minus ion from our sodium hydroxide reacting with our H plus ion in our balanced net ionic equation, forming H2O. I'd like you to balance that. Now, just to prove that we can shift this equilibrium all day long, we're going to add some more sulfuric acid. And give it a mix. And we can answer the questions. The stress we added on the system was H plus from our sulfuric acid. The direction of shift is a right arrow because we have now formed more products and we know the products are orange. And the observation is the solution turned orange. And I will let you answer the last question. What ion caused the shift in equilibrium in this step? In part B, we'll look at the weak acid, weak base equilibrium. To a test tube, we're going to add about 3 milliliters. Again, that's about an inch. The amount is not terribly important, of DI water to a test tube. And then we're going to add 1 drop of the bromocresol indicator solution, bromocresol green. And you will mix and record any observations, okay? Here's the color of that solution. And we know for the first line, the bromocresol green is yellow in its acidic form and blue in its basic form. So the left blank on the top row should be yellow and the right blank should be blue. Okay, the next step, it says, we will add some drops of sodium hydroxide, 2 drops of sodium hydroxide. And we will mix that. I'll help you answer the first one of this, and then you are on your own for the rest of the observation and interpretation. So the stress on the system, we added sodium hydroxide, the Na plus ion and the OH minus ion, and the OH minus ion is the stress that we've added, so we've added an OH minus, and the stress, the direction of shift should be right, and the observation is solution turned more blue. It looks a deeper blue to me. And then explain what's happening in step B5 in terms of Le Chatelier's principle. And we do see via our check, do you see Na plus or OH minus in your balanced net ionic reaction? Yes, we see the OH minus ion. So adding a reactant shifts the equilibrium to the products. Now let's continue on. In step 6, we're going to add 4 drops of 6 molar hydrochloric acid. And give that a mix. I'm going to hold the card up to it. Some of this seems a little bit harder to mix. Let's use our stirring rod for that. I'm going to add 1 or 2 drops more to get that equilibrium to shift. And there, it's shifted now. Okay, hydrochloric acid is H plus and Cl minus. If you don't see either one of those in the balanced net ionic reaction, perhaps it is reacting with one of those species. Mix, record the observations, and answer question QB3. Now this can be disposed of in the sink, and I'll do that right away. Continuing on with our weak acid, weak base equilibrium, we are going to take another test tube, also add some DI water to it, about 1 inch. And then we're going to add 1 drop of the indicator phenolphthalein. And we know that phenolphthalein in its acid form is colorless, and its basic form is a bright pink. Okay, you can answer B11 here, the observation. You can tell whether it's in its acid or base form. And now we are going to add 2 drops of sodium hydroxide. And we'll give this a little mix. And you can tell whether it's in its acid or base form here. You can also answer the next question. B13, what is the stress on this system? We added sodium hydroxide, the Na plus and the OH minus ion. Do you see either one of those ions in the balanced net ionic reaction? And you can tell the stress, the direction of shift, and give me an observation and interpretation. Next, we're going to add some hydrochloric acid. And mix this. And you can tell what direction the equilibrium shifted now. And you can complete the rest of data sheet B. Again, we added hydrochloric acid, H plus ion and Cl minus ion. Do you see either one of those in the balanced net ionic reaction? And if you do not, could they react with one of the constituents in the balanced net ionic reaction? And this also can be disposed down the drain, and I'll do that now. In part C, we are going to look at the equilibrium of a complex ion. So we'll first add 1 pipette full of iron nitrate to a 100 milliliter beaker, and 1 pipette full of potassium thiocyanate also to this beaker. It's going to have a nice deep red color, and then we're going to dilute this to about a total volume of 50 milliliters. All right, we're going to give that a swirl, and then we're going to add some of this to 5 little test tubes. Again, the amount here is not terribly important. We just need to see the color. So we add enough solution so we can see the color. All right, in step 3, it says that the first test tube is going to be used as our control. We're going to look at all the other ones in reference to this one. All right, we know that the Fe3 plus ion is yellow and the complexed ion is red. It's kind of more toward the complexed ion side, so you can answer that question. And now we can start in with step 4. So to test tube number 2, we are going to be adding about a milliliter of iron nitrate. And so about maybe add another ½ inch to that and give it a mix. And we can answer the questions there. What is the stress on the system? Again, you've added iron nitrate, Fe3 plus and NO3 minus, those two ions, you're going to ask yourself, do I see either one of those in the balanced net ionic equation? And if you do, then you're able to write what happened to your equilibrium. If you don't, ask yourself, is it reacting with one of those species? Okay, you can answer the questions from looking at this test tube. Now, in test tube 3, in step 5, we're going to add about 1 milliliter of potassium thiocyanate. We'll give it a shake again. Again, potassium thiocyanate, K plus, and the thiocyanate ion. Do you see either one of those in the balanced net ionic reaction, or could one of those react with one of those in the balanced net ionic reaction? And you can do your observations and data. Record this in your data sheet. This is test tube 3. All right, in our next test tube, this is test tube 4. We are in step 6. We're going to add 6 drops of sodium hydroxide. We're going to give that a mix. We definitely have seen a color change. And let's see if we can get a close-up picture of this, because there is a fine precipitate suspended in solution. All right, so the hydroxide ion forms an insoluble precipitate. So I need you to write that reaction in the R column for the reaction, and it needs to be a one-way arrow. This is not an equilibrium reaction. It is a one-way forming a precipitate reaction. To the next test tube, we're going to add 4 drops of silver nitrate. You want to be sure you're wearing gloves, because silver nitrate will stain your hands for a couple of weeks. It reacts with the enzymes in your skin, forming black dots. We'll give that a shake. I like to cap everything well, so when you pick it up, there's no accidents. I'm going to give that a good shake. Let's look at the color here. I'm going to use my stirring rod. I used this last in part B, so I'm going to give it a rinse with DI water. Now, let's look at this. One of the big questions I get is, I don't know what color this is. Well, is it closer to yellow or red? And I'd like you to pick that. That will help you determine the shift of equilibrium. It's very cloudy, so you can know that there is a precipitate that is suspended in solution here. If we centrifuged it, you will get a precipitate at the bottom. And there's help in this step that the Ag plus ion will react to form an insoluble precipitate. So again, that is a one-way arrow. It's not an equilibrium arrow, and I'd like you to write that reaction too. From this, you can complete the rest of the data sheet, and it looks like that we can read this. I know that these two will definitely need to be disposed into our hazardous waste beaker. I'll do that now. And the other three did not contain anything hazardous, and neither did our stock solution, so I can dispose of those in the drain. In part D, we're going to investigate another complex ion equilibrium, and this one is going to be temperature dependent. The complex ion on the left is called the chloro complex, and the one on the right is called the aqua complex, and that one is pink. The chloro complex is purple-blue. The first thing I needed to do was to make a hot water bath, and I already put water in a beaker, and we're heating that up. In step 2, we need to add 5 milliliters, which is about 2 inches, of cobalt chloride. And it's prepared in methanol. We're going to add that to the first test tube. Let me add a little bit more. And then it says add drop-wise a minimal amount of DI water, and don't add too much, and we're just going to change it to the pink aqua complex. And it's really important not to add too much. Maybe one more drop. Doesn't take much to change it. Okay, one more drop. And just don't really want to overshoot this. It's hard to get the equilibrium to shift back if you've added too much. And that definitely looks like the pink aqua complex. Okay. And then we're going to divide this into 3 test tubes. This is my favorite equilibrium. It's very pretty. It appears that I've used a test tube that I had already used. And there I've divided it into 3 test tubes. All right, so to the first test tube, I am going to add molar hydrochloric acid until a color change is observed. And I'll give this a little shake. And you can answer the questions QD1 through QD3. And again, we've added HCl, the H plus ion, and the Cl minus ion. You need to first see if either one of those ions appear in your balanced net ionic reaction, or if you don't see either one of those, could they react with something in your balanced net ionic reaction. And in the second test tube, in step 6, we're going to place that in a hot water bath. And I'll do that. We'll check that in a minute. It takes a little while. And in the third test tube, we are going to place that in an ice bath. And I've got some ice here. We're going to wait a few minutes and then come back and check these. Now we can check our equilibrium position, and you can finish answering the questions. Here's our test tube that was in the hot water. And here's the test tube that was in our ice bath. From this data, you can complete the remainder of the data sheet. All of this waste here, since it does contain cobalt, will go in hazardous waste. In the next equilibrium, we will look at a saturated solution equilibrium of barium chromate. And this is not going to be a color change. It's mainly going to be looking at a precipitate. So first we'll add about a milliliter of barium chloride to a test tube. Again, the amount is not terribly important. It's about an inch. And then we will add 5 drops of potassium chromate. You can see it's getting cloudy. I'm going to mix it, but it also says to mix with a stirring rod, and I use this for something else. So I'm always going to rinse my stirring rod off first. I don't want anything to contaminate what I'm doing now. Now it's cloudy, so I know there is a precipitate in there. And we're going to need to centrifuge it because we only want to deal with that precipitate right now. And we're going to use a centrifuge, but the first thing I need to do, our centrifuge has to be balanced. It's kind of an older model, maybe even before I was born. We need to put something about an equal amount of water in a test tube in one of the opposite holes of the centrifuge so that it is balanced. Here's our centrifuge. There are 4 holes in here. I'm going to put this in 2 and 4. And we're going to centrifuge for about 20 seconds. And it looks like we have a nice precipitate on our bottom here. There's a precipitate on the bottom. There's still some suspended, but that's okay. We're going to discard that to the waste beaker, the supernatant, or the liquid that is on top of the solid. So I'm going to discard that to the waste beaker. There should still be some precipitate left in the bottom. Yep, there is. It's okay if some of the precipitate gets washed out, as long as you have a little bit. Okay, I've added about 3 milliliters of DI water, and then I'm going to decant this supernatant. And then in the next step, we are going to add about 5 milliliters, 2 inches of DI water. Kind of get the sides here. And I'm going to stir this for about 3 minutes to establish the equilibrium position. All right, we've stirred that for 3 minutes. We can still see that the solution is a little bit cloudy, so we know a precipitate does exist. It's suspended in solution. In step 5, we need to add hydrochloric acid. And we'll shake. And we can look at this now and look at the solution, how clear it is. You can complete the rest of the data sheet based on this data. Okay, now that we're done with this, we can dispose of this to hazardous waste. And we're done with the lab. We can now clean up, maybe give each one of these test tubes a quick rinse with DI water to hazardous waste, and dispose of the hazardous waste in the carboy in the back hood. Return all of your reagents to the tray and make sure that all of the caps are on tightly. Then put everything in the center, ready for the next group. Thank you for being my lab partner today.